climate bistability of terrestrial exoplanets. And then the group of people involved in this work is listed here. There are a lot of people, in fact. It's what we call the Habitability Collective, or the Bistable Collective. And so let's start from the fact that Earth climate is a complex system, is a nonlinear and open system which receives energy from the star and then emits energy as infrared radiation, at least terrestrial planets, Earth-like planets. And so this is the basic thing, but it is not enough because, in fact, there are many other forces acting inside and outside the planetary climate. In particular, we have plate tectonics, which is crucial for Earth. I just remind that Earth is the only planet that is known to have active subduction and plate tectonics at the moment, at least in the solar system. But plate tectonics is responsible for various things, including the recycling of carbon dioxide and the emergence of continents and a lot of things that have been associated to life. The other thing is that we have condensation in the core, which is responsible for the magnetic field, and we'll come back to that in a moment. Let's say 20 minutes or so. Then we have gravitational friction. Again, the Earth is the only planet known to have such a big satellite compared to its mass, which is probably stabilizing the rotation, the axis, the direction of the rotation axis of Earth itself. In addition, on top of that, we have impacts, as dinosaurs know well. And we also have, in the last, let's say, 20,000 years, the action of humans, a species that somehow took control of part of the planetary climate. Because of these many different interacting internal mechanisms and external drivers, climate is varying on all time scales, Earth climate. So apart from the well-known global warming of the last 200 years, if we go back in time, the glacial, interglacial oscillations in the last, let's say, 3 million years, here is depicted the last 800,000 years, we have oscillation between ice-covered, not fully ice-covered, extended ice sheet state, and the interglacials, that the one we are living in now. And if we go even more far away in the past, in the last 60 million years, we see that temperature, the lower graph on the left, has been decreasing in the last 50 million years, with some specific interesting spots, such as the PETM, the Paleocene thermal maximum, about 55 million years ago, but overall a general decrease of the temperature. Right? This I just listed two volumes, a book by Cronin and a booklet by late Wally Brocker on the role of CO2. But apart from what we see here, I mean, the glacial, interglacial oscillation, and we had also other glacial periods before, there was one very extreme episode, which is called Snowball. It has been identified in the last, let's say, 50, 60 years, and studied more in detail in the last 40 years, probably 50 years. About 600 million years ago, there was this period during which the Earth was probably covered with ice, cover which could have been up to 1 kilometer or 2 kilometers thick, going almost to the equator. Now, there is a lot of discussion about the slush ball case, I mean, which the ice left a part of the equatorial ocean free of having contact with the atmosphere, or a real snowball like the one depicted here on the lower right, when the ice really covered everything. That's not clear. There are also alternative hypotheses, but the main, one that is surviving test is the one of the snowball or the slush ball. The other interesting thing, you see it on the left, is that immediately after the Snowball episode, two very peculiar periods in biological history took place. One was the Avalon explosion in the lower part, when the Ediacara fauna was evolved, but then it disappeared and it was substituted later on by the Cambrian explosion that is depicted above, with a lot of very strange animals and creatures that, however, were the progenitors of the organisms that we see today. The CO2 lowering in the atmosphere, probably due to either a reduced volcanic activity or an increased weathering of the surface rocks, due to the fact that most continents were close to the equator, where weathering is more active and more efficient, was the main motor of the Snowball. But the ice-albedo feedback was the one who really set up the transition. This ice-albedo feedback is that when you have more ice, you have higher albedo of the surface. Higher albedo of the surface means less absorbed sunlight, and which means, in turn, lower temperature. So, again, more ice. So this is an amplifying feedback, a positive feedback, that was responsible for, probably, for precipitating Earth climate into the Snowball state. Coming out of Snowball is probably related to the piling up of CO2 in the atmosphere, because the ice blocks the weathering, the surface weathering, but the volcanoes continue to emit CO2 and possibly methane, but mainly CO2, that was piling up in the atmosphere, accumulating in the atmosphere. And then at some point, there was a transition with the explosions, the biological explosions that we have been just mentioned. So we go to Astrobio, and then let's say we know today that there are many extrasolar planets, many of which are of terrestrial type, let's say Earth-like planets. And so can we say something about the climate of these Earth-like planets, the temporal variability of their climate, the possible existence of multiple states, such as Snowball versus normal, whatever it means, and the potential presence of life. Now, you know better than I do that what is followed is the liquid water criterion. Basically, you ask that there is water, there can be water at the liquid state on the surface of the planet. This leads to the definition of an habitability, surface habitability of a planet based purely on astronomical constraints. Distance from the star, luminosity of the star, and so on. On the other hand, we know that habitability is a function of time and latitude. I mean, Antarctica is not really very much habitable, even on Earth. And then the other thing is that interval from 0 to 100, so the temperature of ice to the temperature of water vapor, which depends on pressure, is probably too much for complex life, because most of the enzyme reactions that we know on Earth cease to be really effective above 50 or 60 Celsius. The other thing is that surface temperature depends not only on the stellar output, but also on the planetary climate, in particular on the composition of the atmosphere, on the pressure of the atmosphere, on the albedo, and so on. So not only astronomical parameters, but also climatic parameters of the planet. For what is concerned surface habitability as a function of time and latitude, sometimes they go together with the group of Giovanni Vladilo, Giuseppe Murante, Laura Silva, and others. We defined a simple parameter, which is the habitability, which is a function of time along their orbit and of latitude. And so in the end, the habitability, the fractional habitability is defined as the integral over all latitudes and over the period, the orbital period of this habitability parameter. For example, you can plot as a function of the semi-major axis for a star, which has the semi-luminosity of the sun, on the x-axis, on the y-axis, the logarithm of the pressure of the atmosphere, and you see how the habitability is affected by pressure, semi-major axis, and also the size of these circles tells you about how what is the fraction of habitability from 1, I mean fully habitable, to 0.25 to non-habitable, and so you can define, so to say, a probability of habitability. The other thing, as I mentioned, Laura Silva and co-workers did another work in which, looking at basically the reactions that take place on Earth, you can set the limits more between 0 and 50 Celsius rather than 0 and 100 at 1 bar. This changes with the pressure of the atmosphere, and this, for example, reduces the range of habitability from the left graph, where it's 0 to 100, while here is from 0 to 50 based on these considerations. Of course, the habitability depends on the greenhouse gas concentration. So this is for a concentration in the lower left is the, let's say, 380 ppm, which is as it was about 10 years ago on Earth. But you can see that if you have much lower, 10 ppm on the upper left, or 380 times 100 ppm on the upper right, you see that habitability range moves with the distance from the star. So this was done with a simple climate model that we will discuss in a moment. But the question that I want to start with in order to define these planetary climate models is, how can we describe this complexity of planetary climates? So a well-known graph is the so-called Bredalton or randogram, where you put everything you know about climate and you try to put the links, causal links or interaction links, feedback loops, and so on. And you start saying, I should add this and that and that and that and that. Of course, it's very complicated, but it's what is done currently in global climate models, because we do know a lot about our planet. And in fact, if you look at the development of climate models, and this stops at sometimes at 2010, but then today is even more complicated, the big field started from being purely using pure atmospheric model to something that includes the carbon cycle, the dynamic vegetation, the atmospheric chemistry, everything. So this is what the big climate model is doing now. So what do you do? This is an example of a European model, which is EC Earth, which is a very interesting model because it's open source. It can be studied and downloaded and criticized. It's a big European consortium. So you take this, you take various modules, the atmosphere, the ocean, the chemistry, the vegetation, the land, blah, blah, blah. You couple them through a coupler, which one of the most famous ones is also called OASIS. You turn on electricity and you get something, okay? Something that you have to compare with what you measure. One of the big things of climate models is parameterization of unresolved processes, which means that there are things you don't know about, like turbulence below the resolution of a big climate models, which can be 100 or 200 kilometers, and many other things. The equation of state, the dynamical equations for a forest, or these kind of things. So you parameterize them and you compare them with what you have measured, and then you see whether you did something right or something completely wrong. But when you don't have the data to compare with, then it's a bit of a shooting in the dark. Because climate depends on a lot of planetary details, surface characteristics, albedo, surface albedo. Is it basalt, or is it granite? Is it quartz? Is what? The distribution of continents and oceans. I mean, weathering depends on whether continents are at the equator or at the poles. And the current also, the current in the ocean depends on the distribution of the continents. Atmospheric composition is crucial. As I say, ocean atmospheric circulation, so where are the mountains? Clouds and cloud properties, soils. I mean, there is just a thesis by a master's student that is finishing now, and then we're trying to put different types of soils in an intermediate complexity model. And then the effect of changing the soil is affecting by a few degrees the mean temperature of the planet, of the Earth, because of the latent heat release and of the exchange of moisture. And then finally, what are the characteristics of the vegetation, if there is any vegetation? So in fact, in looking at climate modeling, you have a hierarchy of models. You have the most complex and so-called realistic ones is global climate models, regional climate models. And at the lower end of complexity and realism, you have process models, energy balance models, radiative convective models, and of the like. Typically, complexity and realism increases when you go from the blue to the orange, and understanding typically goes from the orange to the blue. In between, you have the realm of intermediate complexity, Earth system models, very popular about 10, 15, 20 years ago, a little less now. And this can be, there are two views of intermediate complexity models. One is that they are as complex, almost as complex and realistic as the global climate models, and almost as understandable as the process models. This is the positive view. Other people claim, say, that intermediate complexity models are as unrealistic as the process models and as non-understandable as the global climate model. So you choose which camp you like best. For this work, we used a very simple model based on energy balance. So it's the standard old one-dimensional model of developed by various authors in the 60s, 80s, and 70s. Basically, you have the planet, you have only the latitude as the only spatial variable, and time as the temporal variable, and the surface temperature. So you have the first term on the left is how temperature varies, and C is the heat capacity of the planet, of the surface of the planet. Then you have the second term on the left is the diffusion of heat. Of course, heat is not diffused on real Earth. It's transported by turbulence and by large-scale circulations. But in this approach, one parameterizes it as a diffusive effect with a spatial and possibly temporal dependent diffusion coefficient D. X is the sign of latitude. And then you have the I stays for the infrared emission, and on the right you have the solar input. I mean the stellar constant 1 minus the albedo. Of course, I and A, I mean the infrared emission and the albedo do depend on the dynamical state of the climate, while S depends on the inclination, where you are on the orbit, and this kind of things. So the Earth-like planet surface temperature model, which is based on the EBM, has a few parameterizations which add some complexity. One is that the infrared emission is not prescribed as it was in the first EBMs used in astrobiology, but it's really coming from a set of calculations on the atmospheric column, the same kind of model used in global climate models. So we run a lot of simulations, and then there is a lookup table, and the model can go and pick up the correct column to use in a given time step. And the other important thing is that there is a parameterization of the meridional transport, which is based on something that was derived from global climate models, from data using values. This is the meridional transport starting from a paper by Barry et al. In 2002. And then you have various other parameters like the fractional ocean cover. You decide how much ocean there is at each latitude. You do this cloud-free column calculation. Then you add the fractional cloud cover. And then you have the albedo is the short wave top of the atmosphere albedo. I mean, we could spend much more time on the details of this model, but you see that even a model which is almost a caricature of the real climate already contains a lot of parameters which we really do not know what they are in exoplanets. So the parameters that we are considering now are more or less these ones. These have been published a few times, so I will not spend too much time on the details. They are sort of standard parameters for Earth. And the first thing that we do is whether we are able to whether we are able to reproduce the latitude dependence of temperature for Earth. And what you see is that it, by using different values of the diffusion coefficient or of corrections that are in the model, then you get a good reproduction. The gray crosses are the data from the data, and the various curves are these various values provided by the model. Notice a big discrepancy at the Antarctica, but this is, we decided to leave it in because Antarctica, you know, is about 3,000 meters above sea level, while these are calculations at sea level. So if you apply an adiabatic lapse rate correction, then you get the right temperature because simply it's higher, right, than sea level. So let's go to bistability now. Is this simple model able to provide, to give bistability? Well, if you take the same model and you start, this is the lower graph, with the different initial temperature on the planet, what you see is that when you start with a low temperature, you stay at low temperature and you end up in a snowball state, basically 230 Kelvin for Earth. When you start above zero or around zero, let's say not exactly above zero, then the planet goes to a state which is a warm state. The blue straight line and the red straight line, vertical lines, indicate the 0 Celsius and the 100 Celsius limits. Okay, so the model is able to produce bistability for Earth, depending upon the initial conditions, at fixed CO2 concentration, which is the one of today. So what we decided to do, basically, is to explore 100,000 cases by varying eccentricity, obliquity, semi-major axis, atmospheric pressure, and the partial pressure of carbon dioxide. And each of these quintuplet of parameters, for each of the quintuplet, we used more than 20 initial values of temperature to see whether we see something like it is depicted here in the lower graph. The first thing is that putting everything together, you have that there is about half and half of final states that are warm, I mean a little less than half, warm, and slightly more than half that go in the snowball. But this is everything, right? On all the parameters that we used with CO2 fixed. Of course, the more far away you are from the star, the the more probable it becomes to end up in a snowball state. So this is the distance, the semi-major axis distance from the star, and then you see how the warm states disappear. The probability of warm state disappears when you go far away from the star, obviously. But what we are interested in is not so much the overall distribution, but what happens in the cases where there is bistability and whether there is bistability. So looking only for the cases where there is bistability, we find that in fact there are many cases where there is bistability, and some of the states go to the warm state, the red curve, when you start from with a sufficiently high initial temperature, or in the snowball case, when you start from a sufficiently low initial temperature. So this is what happens in the case for the cases that are bistable. So this is the same for the same quadruplet of parameters, but for different initial conditions. Okay, for all the quadruplets of the parameters that lead to bistability. So where is bistability? Well, here comes an interesting, in my opinion, an interesting point. So you see the dot, the circles. The circles indicate the bistable cases, and indicate the color of the circles indicate the probability of ending up in a snowball. And it's again around half or less when you are very close to the star. So you see the region. So bistability is found in a narrow region, but not too narrow. I mean, a very interesting region of parameter space. You have eccentricity in the semi-major axis, because in color there is the habitability index corresponding to that specific case. And what you see, which is interesting, is the fact that when the climate is bistable, well, it's more or less the same region where the planet is habitable from the point of view of the liquid water criterion, which is sort of clear, because in order to have bistability, you must be in a situation where you could have liquid water or not, but at least in the warm state you need to have liquid water. So it's interesting, this correspondence between bistability and habitability. So what are the perspectives? As I say, climate bistability occurs in a limited range, but which is habitability relevant. The most important control parameters are the semi-major axis, the pressure and the eccentricity. And then you can start discussing all the effects of on habitability. I mean, the fact that the metazoans mainly appeared only after the last snowball. Maybe they were there around before, but not occupying very small niches. And so also this can have effects on habitability search, because you find a planet which is completely covered with ice. Well, it can be in a temporary snowball state. It's not necessary that it's always covered with snow. If you had explored the Earth 600 million years ago, you would have said, well, this is a frozen planet. It was, but then somehow it came out of it. The second, the final part of the discussion is that liquid water on the surface is not the only thing that is important. So let's start with asking what makes Earth special. Well, Earth is in the figure at the center, and we have on the left Mars, cold and probably not much inhabited, and on the right Venus, very hot, and who knows whether it is inhabited or not. I mean, I would have said not at all till a month ago. Now it has to be seen. So why is the Earth special? Well, first we have a fluid envelope with water. So this is the important thing for greenhouse, which is crucial for Earth, and for the redistribution of heat due to the oceanic and atmospheric currents. The temperature and pressure are close to the triple point of water. So you have a hydrological cycle with a lot of latent heat exchanged between the different states. You have active geodynamics. The weathering cycle and the carbon dioxide recycling is crucial in order to allow the presence of greenhouse gases in the atmosphere. And then you have continents, and you have just enough water, such that you have some of the continents that come out of the water. Magnetic field from core dynamo allows the presence of life on land. Then, as we said, the presence of the moon, because maybe without the moon, the rotation axis would be moving around quite widely and randomizing the seasons. And then we have a widespread presence of life, which can be a product of those things before, or a characteristic in itself, which is only partially related with the previous characteristics. I will not explore all of them, but I want just to say that the global carbon cycle is a key that should be included in future explorations of exoplanetary climates. The carbon cycle on Earth has two main components. One is the geological, slow one, which is difficult to it's difficult to define the intensity, but somewhere between 0.5 and 2 petagram of carbon per year, and is the one that's related to the subduction. And then the biological carbon cycle, which is of the order of 200 petagram of carbon per year that are exchanged. So much more intense, but superficial. And the reservoirs of biological carbon are much, much smaller than the reservoirs of geological carbon. Just for a comparison, the human emissions in 2014 were almost 10 petagram of carbon per year. And this was a perturbation mainly of the geological carbon cycle. I mean, burning fossil fuel is a perturbation of geological carbon cycle, an imbalance of the geological carbon cycle. Also in part of the biological one, but big came from the perturbation of geological cycle. Life. Well, we know that Earth is a living planet. So much of a living planet that a lot of scientists, starting from von Humboldt, who is not depicted here, going through Wallace, who is depicted in the lower left, to Vernadsky, upper left, to Lynn Margulis, great biologist, and James Lovelock. They were talking of the Earth as, in the words of Wallace, one grand organic whole. So one of the big examples is the fact that the great oxidation event was the appearance of oxygen in the atmosphere, which allowed also the development of probably of complex organisms, was at least in part produced by the cyanobacteria. Probably that was not enough. There were changes maybe in the redox state of the mantle, but certainly the production by the cyanobacteria was a crucial event that, by the way, triggered the big glaciation, the first known glaciation, which is the Huronian glaciation of about 2.4 billion years ago, when the oxygen released in the atmosphere probably removed part of the methane that was responsible for the greenhouse gas at that time. Oxygen does not only changes the environment for biology, but also led to a large variety of minerals. I mean, the mineral diversity on Earth is very large, larger than probably on other bodies, because the waters rich in oxygen circulate in the upper crust and generate new minerals, which in turn host and provide new sources of energy and food for life. So it's really an example of a coevolution of geosphere and biosphere. Some author, like Vernadsky and like Tyler Folk, and more recently, claim that we should not talk of geosphere and biosphere, but really biosphere, because it's really including and encompassing basically the whole planet, at least in the upper few kilometers of the crust. How vegetation affects climate? Well, certainly through albedo. The vegetation is usually darker than the soil, at least in desert, as it is depicted here, the Negev desert. Vegetation exchanges CO2 with the atmosphere, and the evapotranspiration from vegetation is much larger than the evaporation from bare soil, from pure evaporation from the soil without vegetation. So in 1975, Charlie, one of the founders of modern meteorology and geophysical fluid dynamics, developed this mechanism that says in deserts, suppose at some point you have less vegetation, so you have higher albedo. So higher albedo means that you reflect more energy, so you have lower soil temperature. So it means that the atmosphere is less unstable, so you have lower convection and lower precipitation. But since vegetation is water limited, it will be less vegetation again. So this is a positive amplifying feedback, which in reality works not so much at the local level, but it changes the pressure distribution and the monsoon dynamics. So this is one of the important mechanism by which the vegetation can affect climate. Another one, which is related to this somehow, is through the evapotranspiration. Same thing, less vegetation, lower transpiration. So you have reduced moist convection in the atmosphere, lower precipitation, and less vegetation. Same effect, amplifying feedback. On the other hand, from the fast carbon cycle, it could be a stabilizing feedback, because there are various models. One of the simplest is the one by Williamson, Lenton, and others, in which you have three reservoirs: the atmospheric carbon, CO2, the soil carbon, and the vegetation carbon, and then you have various processes that exchange carbon between these three reservoirs. In this case, if you have more vegetation, you have absorption of atmospheric CO2. So atmospheric CO2 becomes lower, so the soil becomes cooler and drier. So there is a potentially weaker hydrological cycle and less vegetation. So it is a stabilizing feedback. So you have all these feedbacks through which living beings and the organisms, and vegetation in particular, can affect climate. So can we see multiple equilibria in the fast carbon cycle? And then you can do a very simple model, not even latitude dependent. This was an old model which was simply 1 point. I mean, there's no latitude, it's one box with 10 variables, 2 soil layer, 2 atmospheric layers. You have temperature and moisture in each layer, plus liquid water in the upper, in the troposphere. And then you have a lot of various feedbacks and mechanisms extracted from climate models and simplified. And what you find is that depending upon the initial moisture of the soil, SD, and the initial vegetation cover, B, you may end up in a state which is bare, with basically no precipitation and hydrological cycle, which is the one in blue, or a state which is vegetated with precipitation, which is the one in yellow, surrounded by the green line. So there may be multiple stable states due to all the feedback that you have been put in this very, very simple model. And also varying, for example, the insolation, the emission, right, of the star, you may have the 2 stable states with a certain difference in temperature, right, almost 10 degrees, but also in one case you have precipitation, while in the other case you have 0 precipitation, and you have various different distribution of the carbon in the reservoirs and so on. So this means that maybe when you do a climate model, you should really consider for an exoplanet whether there is vegetation, because vegetation somehow is building its own niche, even in a way that's a bit more complicated than the DAISY world, but but it is able, through the various feedbacks, to enlarge its initial existence. So the closing comment is that surface temperature is the starting point, but one should consider also other planetary parameters: precipitation, plate tectonics, magnetic field. Biosphere is not a passive traveler. It is in fact creating its own niche, at least on Earth. We forgot about subsurface life, both in water or in the rocks, but one cannot do everything. And the point is that my impression, I come mainly from geophysical fluid dynamics and climate dynamics. Studying the planetary climates and the exoplanetary climates is fascinating, but is also a way to understand, better understand the climate of our planet, and how a climate works, how a generic climate works, so something which we know only in part. Okay, I am done with the talk, with the discussion. I just want to mention that in the working group, Formation Evolution of Planetary Systems, we did something. We didn't do much for various reasons, but and detection of habitable worlds, there was the second line. It's coordinated by myself and Eva Suskiewicz. And then we are planning to write some form of white paper, review paper. We have to decide during the 2021. Could make a small workshop, probably limited in numbers, and hopefully in person, and then a summer school that has yet to be decided whether it will be in person or online. And with this, I think I am finished. If there are questions.
Okay, thank you very much, Antonello. And I would like to then ask people to come forward with questions, please.
Hi, do you hear me?
Yeah.
Thanks. This was a very interesting talk, I think. Actually, I got a couple of questions, but maybe to start with, did you explore the time scale of the vegetation feedback you just showed in the end?
Sorry, I have an echo, so I don't know. Can you repeat slowly the question?
Did you explore the time scale for the vegetation feedback you just showed in the end?
Yeah, we are exploring it now, looking at the albedo. And the idea is to start from the little zero-dimensional model that I was showing and to put it in 1D. Okay. Now, the big problem with that kind of models, I can tell it's some time that we've been looking at that. Surface temperature is not enough. We need an hydrological cycle. So we need to put some moisture in the atmosphere, which is easy to do. But then you have transport of moisture to the poles. And then what happens is that it precipitates as snow or ice, and it stays there forever in the model. Because these models lack a redistribution at the surface like the oceans. So we need to put in an ocean that redistributes it. So we are trying to do that, struggle with that. In fact, we started with a planet was only desert because we were interested in the planet that we call Dune, just to Arrakis. And then the problem is that there is no redistribution, so that doesn't work. We tried that also with the global climate model, but one has to find a way to redistribute in the surface.
Okay, but it would be something which would be active on thousands of years maximum, probably. Or do you expect more millions of years time scales? Probably not.
It's too much echo. Sorry.
Okay, no worry. We can start with.
Yeah, whenever you want, of course. I can try to remove also something if it's my. Okay. Okay, maybe.
Okay, thanks so far.
Of course, I would be happy of discussing with
Any other questions, please?
people who are interested personally, I mean, by email, and then we can set up a Skype, because I think it's interesting to. There is only one paper I know which considered the albedo effect on habitability, the albedo due to vegetation, but I think that many more things can be done, should be done, the carbon cycle in particular.
Some more questions.
If no one else comes up, then I can ask another question, maybe.
Yeah.
Did you explore if there? So at the beginning of your presentation, you showed that Bistability can arise, and that there are parameters, and that there are parameters which drive both Bistability of the system but also habitability. Do you also find parameters which affect the Bistability part, but not what you called habitability index?
Let me try one thing. I try to remove this. Okay. I continue to hear an echo. I don't know why. So we kept the CO2 fixed. We explored different value of CO2. One thing that we should do now is to go through values, a continuous change of the CO2, in order to see whether. Hello? Oops.
I'm still hearing you. Yeah.
Yeah. Okay. In order to see whether you can have a hysteresis cycle. That was not the question, but I just gave the answer to something else because I didn't hear the question. Now I hear you well, so you can ask the question again, please.
The question was if there are parameters which affect your Bistability, but not your what you call habitability index.
Not those that we explored. I mean, the one that I showed are the one that are more important. Some parameters are null, so they really do not affect much neither one nor the other. But I cannot exclude that there are other parameters that affect only one of them, of course. I mean, CO2, I think it's could be one of those. But in the parameters that we explored, this is, I mean, some of the parameters are not very important, but the ones that they affect both. Yeah.
Thanks.
Okay.
There was a question in the chat.
Okay, there is a question in the chat by Nikolai Karavatsky. So, in terms of mid and long time scale effects, where is the input for Milankovitch cycles considered?
It was not. You know, the issue of the Milankovitch cycles is is a different story because it really depends on the details, probably the details of insolation in the boreal areas, and whether snow remains long enough in spring. We did not play with that yet because at the moment we have a very simple model for the ice cover. So one thing that should be done is to put a real dynamical model for the ice cover. The snow is there, but it's simple. So I think that we can safely explore extreme situations like the Snowball and not. I mean, EBMs were able to to reproduce that for Earth. But I think that reproducing the Milankovitch, the response to the Milankovitch, it's an amplification, because Milankovitch is less than 1%, 0.1% total energy exchange, and then the climate amplifies that. And I'm not sure that a simple model like the one that we use is able to do that. But we did not explore it. Milankovitch is for not Snowball, but for a small oscillation of the ice core.
Any more questions, please? It seems that there are not many more questions. I would like to thank Antonello and thanks you all for your participation. We will keep you updated about future online seminars of the European Astrobiology Institute. Please also look at our website, where these are announced always on the home page, and also we'll announce them via Facebook and Twitter. Okay, that was it for today.
Thank you very much.
Thank you very much all, and see you then at the next online seminar.